Welcome everyone. In this video we are going to continue the discussion of the ADS1256 AD converter. So in my previous videos I showed you some parts of the source code or the raw source code, and I showed you how to write the registers, how to read the registers, and how to obtain data and convert it into voltage in order to know what you are measuring. And here we will be investigating these things in a bit more detail, let's say on a bit level. And what this really means is that I'm going to show you what happens through the SPI communication channels, and by studying these kind of signals we are able to see if we are really sending the same commands that we want to send, and also we also check if the timings of these commands are the same as it is required by the datasheet of this AD converter. So I will show you some commands and I will show you what happens. And basically I have a microcontroller which is now not an Arduino but an STM32F103 or blue pill microcontroller, and I have the ADS board, and between these two guys we have the SPI bus, which consists of basically 4 pins or 4 connections, and I will measure basically or acquire the data from this from these 4 connections by using an SPI analyzer. And you can already see the recorded signals from these kind of channels. So let's jump into this, and I show you what is what on this screen. So you can see that here we have the signals, but what are they in these SPI channels? So let's start with the first one. So the first one is the D in or data in pin on the ADS. So this is data in, or the master out slave in on the microcontroller, and this is the other part of this. So this will be the D out. This is where the data comes out from the ADS, and master in so goes into the microcontroller, and slave out. So slave out is the D out basically, and slave in the data in. And then the next, I think it's quite obvious from these patterns. So this is the clock, and then this is basically the chip select or slave select signal here. So you can see that it goes low when we start to communicate with the ADS, and then it goes back high when we finalize the SPI communication. And then here we basically just have the data ready pin, and that's all. So we now neglect this because I just left it in the software, but we don't do anything about that. So let's see what we have. I copied this picture from the datasheet, and it shows you how to do the communication if you want to read a register. And let's say in this case what I'm showing here is we are reading the register 0, so a reading register and the number 0. So what happens here? So first of all we have to know how to read the data from here. So we want to see either the data in or data out, and also the clock. So whenever there is a clock sequence here, so this is one clock sequence, we have to see what is the value of these SPI channels. So what is the value here, and or level, and you can see that this is high level here, that means it is 1, and you can see that here we went down to low level and it's 0 when there is one clocking here. And now we don't read anything back from the ADS, because we are now sending the command. So at the first part of this signal, we only take care of this channel here, the D-in channel, so the uppermost line. So let's see what we have. So we start here, let's say here, and then this is 0, 0, 0, and here we have 1, because this is up here on the high level. And then again we have 0, 0, 0, 0, and we finished the first command byte here. And immediately I suggest that we should study this. So what we have here is basically 0, 0, 0, 1, 0, 0, 0, 0. And what this means is basically we have this is maybe a bad example, but we have the read register command, which is the same, and then we also have the 0 included this, because when you send the first command byte, that also contains not only the command itself, but the value for the register address. So in this case we have only zeros. And then that's how you got. So this is 0, 0, 0, 0, 1, 0, 0, 0. And then you have the one here, as you can see. So we put together the two commands and we got this. I will show you a different example later where it is more obvious that this is two commands combined together. But you can see that the first command is done, and we go to the second command byte. And you can actually neglect this. So as you can see that whenever we have a clock sequence in these parts, we have just 0 everywhere. So we neglect this because we just want to write one simple or single register. So then another critical thing is that we can check the time between these two guys here. And basically this should be the T6 timing, and here I managed to get it to 6.3 microseconds. And that is like almost around 6.5-ish microseconds, which is required by the datasheet. But as you can see, the command is written and then or read, and it reads back the correct numbers. So it seems like 6.5 is also enough. It's a bit difficult because with the microcontroller you can only define integer numbers for the delays between the commands to the SPI. So that's one part, and also when you send or receive through the SPI, that also takes time. So you have to sort of experiment with this to get as close as possible to this recommended timing here. So that's all about the timing. And now you can see that the data in goes up because we start to fill in the register with some dummy data, and so you can just send full ones. But what is interesting now is the second line, because we are starting to read out the data. So as you can see, when we clock, the first two clocks are 0, and then here the third and the fourth clock gives us 1 for the D out, and then another 0, 1, 0, 0. So then this is the result, and if you convert this to a decimal number, then this will be 52. And if you check the datasheet and compile the numbers for the status register, then you can see what is my setting for this register. And of course we can cheat, because here in this sequence we already have these data converted, but I wanted to show you if you don't have this let's say translation from your signal to the actual hexadecimal or binary numbers, then you can also just do it manually, because these are not too many signals. And we got back the same as it was translated by the software. So this is done. So this is how we read a register, and this proves that my code works, because yeah, it gives back the same thing that I want. So now let's jump to the writing part of the register. So let's write down the legs. So this is data in and data out, and then we have the clocking sequence here, and then chip select or slave select, and then here we have the data ready. So again, I write down the command that we want. So we want to write register. We want to write the third register. So this is the address, and then the value of the register should be 99, which will instruct the AD converter that set the data rate register to 99, which is 50 SPS sampling rate. So let's do this. We start with the first command byte, and then here we start. So 0 1 0 1 0 0 1 1. And now I can show you a better example than here for the combination of the two things. So we have these write register and 3 combined together. And how? So let me show you. So we have the original number 0101 0011, and then this is basically the combination by the OR operator from the following. So the write register command individually is 0101, and then this can be all zeros, the last 4 bits. And then the 3, I mean, if you translate the binary to decimal or vice versa, then this is basically the binary equivalent of 3. And then you can see that we combine these two together with the OR operation. So this will be 1, this will be 1, 0, 0, 1, 0, 1, 0. So we get back this number here. It's very simple. So if you see this, then this is the write register part of the command, and this is basically the address part of the command. And then again we have a byte equivalent of zeros, because we neglect the second command byte. And here we don't need any delay. If you can see, there is no delay, as in this case, like T6. So we just move on and see that this is 0 1 1 0 0 0 1 1. So without any delay we go to the next data byte, and this is, of course, is 99, because we wanted to write this. So then the data is written to the register, the chip select goes back, and the data ready is just jumping to high. So this is basically, let me go back, so this is the second byte for the command, and this is the value, and basically that's all. So this is the reading and writing part for the registers. And also we neglect this as well, because we neglected the second command byte, so we don't write the second register. But in fact you can write 2 registers at the same time if you want. So let's jump to the next part. So in this part we are going to read one single data from the converter, and this will be a conversion value. So here we will be using the RDATA command, and we will read one value only, so just one conversion, as it is shown on this sequence from the datasheet. and the multiplexer is already set up. So we really only focus on the conversion, and that's all. So what we can see here is we can just define the pins or the signals again. So D in, D out, and then clock as well, and chip select and data ready. And here we have basically the translated data for the SPI, but we do it manually just to practice. So this sequence says that if the data ready goes low, which is already low here, then we can send this command, and you can see that this command is already sent here. So this is the RDATA command up here. So we sent that, and after that we are waiting, so there is a delay, and then here the time is approximately 6.83 microseconds. I measured it, and this is roughly the same as the T6, so we are fine. And the datasheet says that the minimum value should be at least T6, so if we wait more, then we are still fine, but I guess we cannot wait forever. But yeah, we are close to the T6, and that all what matters. And here the sequence shows that after waiting T6 the clock restarts here. So we get the clocks, and then we get the most significant byte, the middle byte, and the least significant byte. That will be the last clock sequence, and after that the data ready will go back to high, which we can already see here, and that's all. So this was one command sequence. So first of all, what we can see here is that until this we have the MSB, or down here, and then until this we have the mid byte, sorry, so this should be mid, and then of course the rest of this is the LSB, or least significant bit or byte. What we see here on the D in, we just push in dummy data again just to do something. So we don't care about the D in now, because we already sent our command, and that's the only thing which is required on this command sequence. So we go to the second line and start to translate. So 0, 0, 1, 0, 1, 0, 0, 0. And I start also with some kind of thing which I already showed you. So how we can combine this 3 times 8 bits into a 24 bit number. So what we have is that we have some kind of variable which is already filled up with let's say 24 zeros. So it is like this, and these are just separators, these lines. So we have the first part, the middle part, and the last part of this. And what we do, that we read the first part, the most significant bit, and then we start to shift in the we shift out the data from the register, and we start to shift it into our variable on the microcontroller. So what happens on this part here is that we receive the most significant bit, and we use the OR operation here. Now I write it, this is OR and not a separator. So the MSB, so basically this number here, this number here, the purple one, is getting combined by using the OR operator with these zeros. So what we will have is that we still have zeros here, we still have zeros here, and then we fill in the number here. So 0, 0, 1, 0, and then here we have 1, 0, 0, 0. So this happened now, And what happens now is that we have to shift this. So I write just down. We have to shift this towards the left by 8 bits. So what will happen, this stays 0. This will be this number here. So 0, 0, 1, 0, 1, 0, 0, 0. And then this is full zeros. And now we have the mid byte. So the mid will come here. So we see that this is 1. Sorry, I write it here. So this is 1, 0, 1, and then 0, 0, 1, 0, 0. So basically this number here will take up this space. So we have to combine again this part. So basically the MSB with the mid byte, or this is basically the shifted MSB with the mid byte. So we have this. So the next number will be 0, and then we keep this same number here. And then here comes this guy here. So 1, 0, 1, 0, and then 0, 1, 0, 0. So this is fine. And now again we have to shift this number by 8 bits. So this guy here becomes the first row or column, first column, and then this guy here becomes the middle part, and then we have zeros here. And now comes in the LSB. So let's read it. So this is 1, 1, 0, 0, 1, 1, 0, 1. So what we have at the end is the following number. So this guy here. And then we see that the MSB took the place here, and then the mid byte took the place here, and the LSB took the place here. So now we can convert this into a decimal number. So we are done here, and also we see data ready went back to high. So this part is finished. So the decimal value of this is the following: 2663629. And then we already learned how to convert this into voltage, but just if you open up the data sheet, you can see that the voltage, which I will use with U, is basically the VREG divided by 2 to the 33rd power minus 1, and times, let's call it B, which is now the bits, sort of. So if we do this, we know that the VREG is 5 volt. We get 1.5876 volts. So this is the final result. And actually I took a picture of a multimeter measuring this circuit on the same input, and as you can see, it is showing a very similar number. So this is what happens basically in the microcontroller as well, or you can make a software on your computer, as I did, and do this kind of calculation when the conversion on your computer, so you save some resources on your microcontroller. So basically you send out the RDATA command, wait a little bit, and then you receive the MSB, mid byte, and the LSB, and at each let's say receiving sequence, you have to shift the data, so at the end you will get your number in the proper order, which is visible down here, and then you just send this towards the computer, or you can convert it on your microcontroller as well if you have enough resources, and just print the final value after the conversion. And that's all. So again, we can jump to the next part. So this is a bit more complicated thing, because now we are cycling through the input multiplexer while continuously reading the output of the AD converter, but it's not that difficult, so you can do it, or we can do it. So here again, just to see what is what, I write here the names of the channels or the signal lines, and then I already put in a few things like the multiplexer values if you want to combine two channels together, and here I'm using the channels in a differential mode, and also I put here the most important datas in bits, so you can see them because we will use the things here. So let's start with the command sequence. So we can like separate these things, at least based on the clock, so we can see the data in a bit better way. But let's do it until this part here, because this is basically the writing sequence, and then you can see that the D out goes low, so we start to have something with this clock sequence. So first, let's see what we do here. So let's see this. So 0101. So this is a writing register command here, and then we have 0001 here. So this tells us to write the first register, or the number 1 register, because the first one is the register 0, which is the multiplexer register, and then this should be the second command byte, which we neglect, so there is just full zeros here, and then we have another value here, so 01 0 0 0 1 0 1. So as you can see that this is the setup of the multiplexer, and what it says is basically this guy here. So at this part of the sequence, after data already went down, so here we started to write the register, and then we used this value here, so basically this guy. So this is done, and now we go to the next command. So immediately we have to issue a sync command, which is up here, and we can clearly see that we have 1 2 3 4 5 6 ones and 2 zeros, so we are done with the sync. And then soon after this, the data ready should go up, which is done, and we have the wake up command now. And as you can see that we have 1 2 3 4 1 2 3 4 ones, so this is the wake up. And in fact, if you check the data sheet, this can be this as well. So the wake up in one of the tables is defined twice, and in the first part of the table is full zeros, but you can also send full ones, and what I did here is I sent full ones. So let's say until this part here we have this guy, and then this part here is the sync, and then here we have the wake up. So once again, this can be also full zeros, but here I used full ones. And now we have to send the RDATA command, and we can see that we have 0 0 0 0 0 0 0 1. So we are fine. The RDATA is also here. and we should receive our data immediately, basically, or as soon as the data is ready for reading out. So actually now we have to read the second line here, and these are again just dummy bytes here all across this part. But then here we have the numbers, so this is 0, 0, 0 and 1, 1, 0, 1, 1, and then 0, 0, 1, 1, 0, 1, 0, 1, and here we have 1, 0, 1, 1, 0, 1, 0, 1, and then we can do the same and convert it into decimal number. So that will be 1783221, and if we convert this to voltage, then this is roughly 1.06 volts. And I measured another input, as you can see, so the A in 4 and A in 5, and I checked this with the multimeter and it's the same, so it still works. And what I have here down is just, as you can see, the same data sequence over and over again. And what we have here is that we can just measure this time, for example, or between the data ready, it doesn't really matter, and measure the time or the frequency, and this is 825 Hertz frequency. And if you check the data sheet and check one of the tables, in this case the table 14, then you can see that if you have set up 1000 Hertz as data rate, which I did, the cycling throughput should be 837 Hertz. So seems like this is quite close, so we can accept that our timing is more or less good. And as you can see that we have a lower frequency, so that means that somewhere we lose some time. And if you think that we have to write registers and we have to receive data and also send it, for example, to the computer or something, that can be accounted for the extra time. So we can accept that we have a slightly lower data rate. And this also suggests that we can also improve the code a little bit if we need that 12 extra Hertz. But it doesn't really matter at this time, and I will show you later that more or less we have good timings. So let's jump to the next part now. So this is basically the last sequence, and here we have the data in, but we neglect this because also we don't really have anything here. So we have the data out, and of course the clock, chip select, and the data ready. So first of all, why you don't see data in is because this is just the middle of acquisition sequence. So I just took 3 signals, I took 3 like packets of signals from the middle of the measurement. So you don't see the initial thing, but you can see is that we always have data, and you can also see that yeah, of course we have clock. Chip select is low for the same reason, so I already set it low in the beginning of the measurement, and data ready is going down if there is a data is available, and going up, so it goes low and it goes high according to basically this figure up here. So we already started the measurement, and let's say the data ready goes low, as in the case of this part. So we sent in the data or the command, so this RDATAC command, somewhere here, it doesn't matter, and we started to receive the data. So after the very first command we had to wait T6 and we received our 24 bits, and we don't have to do anything after this part. So the data ready goes up, and then when there is a new data available, so now we really start with our chart. When the data ready goes down here, then we just read out the 24 bits, and that is what's happening here. Now I don't translate it to a number because now it doesn't matter, but that's what happens here. So then the data ready will go up high, and then we have to wait something, some values, and actually here it will follow this command sequence. This will be like this, and then here again we will have the 24 bits again, and so on and so on. And that's what we see here. So after some certain time, which is of course should be the time which we set for the data rate, the data ready goes down, and then we get our data, and after the conversion or reading the results, the data ready goes up, and then we wait again, and so on and so on. So you see that data ready goes down, we read the sequence on the D out, and then data ready goes back. And here we can measure the time, and the time is 133 microsecond, or okay, to be more precise, is 333 something microseconds, and this is actually 7.5 kilohertz. And I set the sampling rate to this, so in this case the timing is actually perfect. So seems like that in the previous part I messed up the timing with either sending and receiving the data or something else, because here if you let the device do everything by itself, which in this case means that after there is data ready, then the data will be available on the D out for shifting it out, then in sort of automatic mode the device works well. But if I have to send data more often and I have to cycle through the registers manually, then there is a slight delay as compared to the values in the data sheet. So here you can see. So here I just wanted to demonstrate that this, let's say, automatic output of the data works very well, and also the timings between two data ready is according to the data sheet. So this was all basically. So I showed you how the SPI communication works on a more lower level, and you could see that we can translate the signals to binary and then decimal numbers, and then finally we can convert these numbers to voltage values, so we can actually use this AD converter for the intended purpose. And this is really good because if you can do this, so reading the SPI, you can fine-tune your code and you can check for errors as well. So for example, you can see that your timing is not correct, or you can also see that the data is not written to the registers that you want to read, and so on and so on. So this is a very useful device. I just put the link in the description so you can check and you can buy it if you want. But yeah, this was all regarding the SPI communication. So see you in the next video.